at the Graduate School of Universitas Gadjah Mada. We are honored to have a special delegation from Taiwan University with us today, Professor Huang Chi-chuan and Dr. Yang Chi-chiang. Before we start today's guest lecture, allow me to read the rundown for today's event. The event will begin with playing Indonesia Raya and then followed by a welcoming address from the Dean of Graduate School. And next we will hear a speech from the head of Ginju Information Program. Then we will proceed with the main guest lecture by Professor Huang, followed by Q&A session. And after that, we will be a guest lecture from Dr. Yang Chi-chiang, also followed by Q&A session. And then finally, we will have conclude with closing remarks and appreciation for the speakers. Now we will listen to the Indonesian National Anthem, Indonesia Raya. And ladies and gentlemen, please stand up.
Exploring dynamic landscape through digital terrains and high-quality field observation. And I think this is very important as Indonesia, as you know, we have many islands with many different landscape and also terrains. And thank you for Professor Huang Chi-chuan and also Dr. Yang Chi-chiang. Yes. We would like to inform you that a graduate school is running 25 study programs. interdisciplinary study program consisting 14 master programs and 11 PhD programs. And the teachers come from all faculties, like Prof. Juru from background is geography, but he is in the agriculture faculty, and I'm from faculty of engineering, civil engineering, majoring in transportation. And I've been the dean here since 2017, not 19. Yes, we do hope that not only the student can learn, but usually students have experiences also. So we can exchange knowledge, experiences. So after this, that we can have more understanding, and then we can do better for the career of every student and also the development of the institution. And hopefully we will have enjoyable and fruitful guest. And thank you very much. Good morning.
Thank you, Professor Siti Mahkamah, for the warm welcome and inspiring words. Before we dive into exciting presentation, let me first introduce the person who has made this event possible. Please join with me in welcoming Professor Juman Santani. To the head of the Geoinformation for Disaster Management and Spatial Planning Program, and the person in charge of today's event to give the opening remarks. And please, Professor Siti Mahkamah, to take a picture with Prof. Junun and the speakers for the opening remarks.
Assalamualaikum warahmatullahi wabarakatuh. The Honorary the Dean of the Graduate School Universitas Gadjah Mada, Professor Siti Mahkamah, and the Honorable guest lecturer, Professor Huang Ji-chuan and Yang Ji-chuan. I'm sorry for mispronouncing your name. I'm not used to pronounce the Chinese name. and also the distinguished guests and gentlemen who like to attend this general lecture from my colleagues from NTU Taiwan. I want to mention that the audience is not coming from Gajah Mada. Actually, there is one professor from Tanjung Pura from civil engineering also. Yeah, and also from other university from UPN Veteran Yogyakarta. Also, I saw, and maybe from Akprin, yeah, also somebody attending this lecture. I'm sorry I cannot mention one by one of you all. This is today we are very honored to have lectures, general lectures. Of course, we have experience. They have experience. This moment, so we will share our experiences. They have different insight of the research in terms of erosion, weathering, and nutrient transport in the scale of watershed. So we are already accustomed with the watershed management, erosion, and sediment transport, but we will see the achievement of the research from NTU Taiwan. And also the landscape dynamics, also we are studying landscape dynamics in Indonesia, especially in Gajah Mada under the program of geoinformations and spatial planning and disaster management. Yesterday I took them to the volcanic landscape and I show to them general pictures of our landscape dynamic due to the natural processes, very dynamics, mainly by volcanic eruptions and also by human activities, interrelationship between the natural processes and human activities is always becoming very big concern for us.
National Taiwan University. Professor Huang received his PhD degree in National Taiwan University and his research interest was hydrogeomorphical process simulation in catchment scale. After receiving his PhD degree, Professor Huang worked as a postdoctoral at Biodiversity Research Center and Research Center for Environmental Changes in Academia Sinica. Recently, he focused on carbon cycle, nitrogen cycle, and watershed management. Professor Huang is highly respected expert in his field, and today he will be sharing his knowledge on the topic of erosion, weathering, and nutrient transport in Taiwan. Professor Huang, the stage is yours.
presentation contained these 5 parts. The first part is my self-introduction and then the background in Taiwan. I hope some of you may be interested to study in Taiwan, and therefore I put this part in my presentation. And the third one is the erosion, the fourth one is the weathering, and the last one is the nutrient transport. Okay, from the self-introduction, my name is Zhichuan Huang. Huang is the family name. Zhichuan is my first name. I know it's very difficult for everyone to remember. In Chinese, this name means remember the river. So my nickname is River. And because of my name, so I need to do the hydrology to make money, you know. So I'm a hydrologist. For me, my study is doing the water cycling. So I always study the water cycling within the watershed. We all know that we have the water from the precipitation and then have the overland flow to be the stream flow and go to the sea and then evaporation and run and run and run. That's the water cycle. We learned it from the elementary school, right? And in fact, in human body, we also have the water cycle. We drink the water and then we evaporate the tears or out of the water from our systems. So why that's so important? Because the cycling itself indicates the forever, you know. If something can cycling again and again and again, which means that the system can sustain forever. Which also means that if we want to keep our environment sustainable, you need to keep it running, right? That's why my research focus is the water cycling, particularly for the cycling. And the majority of my lab work is quite simple. We just go to the field anytime. Perhaps the daytime, the nighttime, during the typhoon, during the winter, during the summer, every time I will always take my students to the streams and we take the water. We just take the water and back to the lab and to do some analysis, put the water into the machine, something like we go to the hospital and the doctor always take our blood to test the quality, right? Test the index. So it's very similar to do the work that we did in hospital. And once we take the water to test its quality, the water quality, then we will know what happened within the watershed, right? Because the water, in fact, is washed through the whole watershed. Once it washed, it will dissolve the many materials and carry the materials into the stream. And then once you can detect the water quality of the stream water, then you will know everything from the water sample. I think it quite makes sense as what we did in hospital. So the majority of my work is that we took the sample and then we analyzed the parameter within the water, and then we try to understand all the process happened within the watershed. That's my main work. And this photo is taken from the midnight during the typhoon sampling. Probably everyone knows the typhoon. Typhoon is a tropical cyclone and always westernward to the Taiwan, and it always blow the strong wind and the torrential rainfall to visit the Taiwan. In fact, the past 3 couple days, there is a typhoon just visited Taiwan, and so far he brought around 2,000 millimeters within the 3 days in the southern Taiwan right now. So it's a very special case of very extreme events to tell us if once we want to face the environmental hazard disasters, how to do it to prevent such kind of risk. So that's my major work for the work in Taiwan. And as you know, because I do such kind of work around 20 years, so sometimes we have some collaborations with Austria or Japan, and sometimes some papers will want to, if they want to know something, they will ask some materials from my labs. For example, here this study is talking about the typhoon track and what's the consequence from the rainfall and the precipitation spatial pattern and then the hydrograph. And this is from the nutrient transport, something like this. So if you have interest, you also can find those studies from the website. It's not very difficult to find. Okay. And then let's back to the environmental background of Taiwan. Taiwan, in fact, is quite similar to Indonesia. We also located between the two plates. One is the Eurasia, the other is the Philippine Sea Plate, and we are on the arc collision areas, which means that the mountains in Taiwan is still upper and upper. Although we have some volcanoes, but our volcanoes is inactive. Unlike yours, you have the active volcanoes. Yesterday we just visited the volcano Merapi. It's quite very impressive. I cannot imagine such kind of volcano can be so active. But nevertheless, let's back to Taiwan. We are located on the arc of the two plains. Therefore, we also have many earthquakes, fewer typhoons. But the most important is that, in fact, Taiwan is still upgoing because of the collision name. The mountains is still going. The uplift rate is around 6 to 8 millimeters per year, getting higher and higher. On the other hand, the horizontal movement, it always squeezes Taiwan close to the mainland China. Perhaps we don't like it. It's around 70 millimeters per year, getting the whole island move eastward. And such kind of tectonic activities make the Taiwan landscape is very steep, and the geological formation is very fragmented. And here is the typhoon, like the Indonesia. In fact, there are numerous earthquakes in Taiwan. Here is the location of the earthquake center. You can see that almost every year, almost every day, everywhere we have the earthquakes. And the earthquake result is something like this. But I think it's a disaster. But in fact, it's not very bad, because there are only few deaths caused by the typhoon. 25 years ago, we have a big earthquake called Chichi earthquake. That earthquake was located in the central Taiwan, and that earthquake caused around 600 deaths. It's a very terrible and serious one. At that time, our government protect the buildings. They set a very strong regulation to strengthen the building. And since at that time, our building capacity is more and more stronger. It's stronger, therefore, the building so far, once we face the big earthquake, so far I think it's okay. And another environmental setting characteristics in Taiwan is the precipitation. Like the Indonesia, we also have abundant precipitation. The annual precipitation is around 2,005 millimeters per year. But unlike the Indonesia, we have the typhoon. Typhoon is a very concentrated precipitation with 2 days, as I mentioned before. Therefore, here is the typhoon track from the tropic to the West Pacific, and you can find that there is the strongest area around the world. So, which means that Taiwan, internally we will say that we have a very active tectonics, and outside the environment we also have the tropical cyclones. Therefore, such kind of the fusion makes the landscape in Taiwan very special or quite unique. So here is the disaster caused by typhoon. We have the flood, and you can see that the strong wind will destroy everything. And in the mountain area, we will have the landslide and the debris flow. It can merge even the building or everything. So in this regard, I would say Indonesia and Taiwan probably we also have the quite similar environmental settings. One is the tectonic activities, the other is the precipitation. Such kind of the two fusion is very important for shaping the landscape. That's why I think the landscape evolution or characteristic in Indonesia and Taiwan are quite similar. So let's move to the summarize the environmental setting in Taiwan. Here is the background that I mentioned before. We have the abundant precipitation, and solar radiation is also very strong. Therefore, we have the annual evapotranspiration around 800 millimeters, and we also have numerous mountain areas. And also, we also have a lot of people, but not as many as yours. So, under such kind of the environment, let's back to the erosion. Erosion, in fact, is the product of the God from my personal view. Because once you have the mountain, the God will shape the mountains and transport the sediment into the plain area and then into the oceans. They will cut in the mountains to make the land more flat. So, from the global perspective, you will find that our area, the Oceania Islands, is the majority of the sediment source around the world. We contribute around more than 60% of the sediment. And in this area, if you take a close look, you will find that Indonesia and Taiwan are the majority of the sediment contributors. So if we want to know how the sediment transport globally, I think we need to from the Oceania Islands, from Taiwan to Indonesia. And then, based on this kind of the sediment transport, we developed a model to incorporate the surface soil erosion and the landslide sediment, and then we estimate the whole sediment export globally. And here is the result. You can find that this area is the main contributor to the oceans, and the Andes and the India probably is the second one. So such kind of the model tell us that not only the soil surface erosion, but the landslide is the majority of the sediment to the oceans. And here is the landslide. Once the landslide occurred, they will transport all sediment into the streams, and it will make the stream water muddy, right? And the degree of muddy, we also call it sediment concentration. In fact, is the function of the landslide area. Once your landslide area increased because of the typhoon or earthquake, the concentration will increase. After that, if the landslide has been recovered by the vegetation, then the sediment concentration will decrease. So it's quite a very dynamic the concentration of the sediment with the discharge is dynamically with the landslide areas. So which means that if you want to estimate the erosion or the sediment export, you need to understand the landslide patterns in your regions. Otherwise, you cannot estimate the sediment export pretty well. And here is another case in our Zhousui River. Zhousui River located in the central Taiwan. And here, there are two tributaries. One is full of the landslide, the other is only one big landslide, and we just want to see the sediment export in these rivers. And here is the case of the left tributary we call the Qinshui Xi. Here is a dam, but this dam is blocked by a landslide because the landslide always slump a lot of the landslide and block the streams. So here is the lake. The lake just stand for 5 years, from the 1999 to 2004. And during 2004, there is a typhoon, and then he destroyed the dam, and all the water and sediment were transported downward. And then, after the typhoons, here is the new landscape. It's quite dynamic if you see the time. Here is 2004, June, 1st June, and this is the 24th November during the 2004. Just 6 months, all the landscape changed quite a lot, which also means that even if we don't take a close look on it, in fact, the landscape changed a lot, and such kind of the change also will affect the ecosystem. The ecosystem service is the main source that we take from the nature world. So I think it's very important. And here is the overall sediment exported in Taiwan. You can find that this is the most important one from the Erlen River, and all the sediment exported in Taiwan is dominated by typhoon. So once the typhoon comes in, our sediment export is as large as the Mississippi rivers or the Yangtze rivers. It's relatively comparable. So it's quite disproportional. I think that's the main characteristics of the mountains rivers from the Oceania. And such kind of the landslides, they probably just stand or just temporarily stored in the hill slope or near the streams. So we developed a model which considers such kind of the sediment storage to simulate the landslide area and the sediment export simultaneously. I call it the dual simulation. Such kind of the model, it can simulate the landslide area and also can simulate the sediment discharge together. And we evaluate it in Taiwan rivers. So far it looks good. So I think it's possible maybe we can take this into the Indonesia rivers to see such kind of the model and to see the characteristics or the difference between Indonesia and Taiwan. And here is the response surface. One thing is the rainfall factor, the other is the landslide area. Based on the two parameters, we can estimate the sediment exports simultaneously. So, the basic finding of this part, I just want to say, for the sediment export, the rainfall, available sediment, and the discharge are the key controlling factors regulate the sediment delivery. And here is another case for landslides. This is a mountain, and here is a village. After typhoon, all the mountains, all the materials on the hill slope will just slump into the rivers and submerge the village. caused around 300 deaths. So it's a very huge landslide. So our scientific question is want to ask, how long it will take to recover the ecosystem? There are so many landslides, and one hand they will export the numerous material. On the other hand, they need to recover the ecosystem. So this study is just talking about how long does it need to restoring the ecosystem. And we use the satellite data to collect around 5 decades and take the soil samples and the litters, and finally we got this consequence. So we know that for the soil, organic carbon is kind of the nutrient. It may need the 5 decades to restore this land. However, in terms of the litter fall from the reef, from the forest, is also the main nutrient from the ecosystem. It may need 3 to 4 decades, 3 or 4 decades to recover such kind of land. So, which means that if we want to take a land for any other purpose, and one day you think that you will treat the environmental friendly, you want to take it back, at least you need 3 or 4 decades. It's a very, very highly costed. So, after erosion, we are only talking about the sediment. On the other hand, we want to talking about the weathering. The weathering, it means that the rock will from hard to soft. It will change the chemical properties. Most of it is the dissolution. Because when the rock meets water, they will dissolve some ions into the water. That's why our sea is getting salty and salty, right? And that's why our soil can gather the fertilizers. And recently people find that such kind of dissolution will reduce the carbon dioxide from the atmosphere, because carbon dioxide can become the carbonate acid and can help to the weathering, which means that if you can enhance the chemical weathering, then you can absorb the carbon dioxide. And this is a hard issue that the many scientists want to work on it, because if you can put some silicate on the field, then it will absorb some carbon dioxide. So we also use the same way to evaluate how much carbon dioxide can absorb it during the rainfall runoff processes. And we found that the rainfall and runoff, as well as the physical erosion, are the key factors to regulate the chemical weathering. Then we want, based on this understanding, we want to see how it changed in Taiwan. So here is the result of the Taiwan. You will can find that it's consistent with the previous study. The runoff and the physical erosion are the main drivers to regulate the chemical weathering in Taiwan. That's no problems. But the question is that from the global perspectives, the chemical weathering, the pattern of the chemical weathering is something like this. You will find that for mountainous area, or for the abundant precipitation area, the chemical weathering is very active. Which means that it's a hard spot to absorb the carbon dioxide from the global perspectives. And during such kind of the region is almost around 10 times than the global average. However, in mountain building regions like the Taiwan, not only the chemical weathering not only can absorb the carbon dioxide, however, because we have some pyrite, some sulfate, such kind of the sulfate will stop the carbon dioxide from the atmosphere. So during some models, we can calculate the net carbon dioxide absorption in Taiwan. And we also find that in Taiwan, the chemical weathering is very strong, no problems. However, the capacity of the carbon dioxide is not expected high as previous study documented because of the pyrite oxidation will stop our absorption of carbon dioxide. So, this study we want to tell others, chemical weathering, the strongness of the chemical weathering is one thing, but the carbon dioxide absorption is the other thing. It's not the highly strong, it's not a highly linkage. You need to separate it to discuss, to evaluate how much carbon dioxide can be absorbed. It's totally different. It's totally different. And the third topic we want to talking about is the nutrient transport. The nutrient transport, I think the main risk of the nutrient transport is the eutrophication. Eutrophication in most water bodies may be the main challenge around the world so far. And it also is the main source for the dead-zone expansion. Here is the dead-zone expansion. And the so-called dead zones, which means that the dissolved oxygen is less than 2 milligrams per liter. 2 milligrams per liter, which means that at that time no fish can live in such kind of environment, and that's why we call it dead zone. So, like the eutrophication, once the dissolved oxidation is less than 2 milligrams per liter, then all the ecosystem, aquatic ecosystem will be destroyed. So I think that's the very serious threat so far. And the main reason why the water body will be eutrophied because of the human activities, livelihoods and the fertilizer. That's the main causes to make the eutrophication. So in this regard, we use the GIS technique. We have the precipitation data, we have the population data, we also have the land use data. Such kind of data can help us to calculate the nitrogen budget, the nutrient budget. The land use data is very useful because we know that the fertilizer application corresponded to each kind of crops. And then once we have the land area, we can estimate how much fertilizer that we are used. So land use data is very important. So far, numerous studies prove this point, no problems. And the population is also important because the people will have the metabolism and we will release some nutrients to the water. That's why if we know the populations, then we can estimate how much nitrogen will be released. And the first one is the environmental background, that's the rainfall. Because the nitrogen also sustained in the atmosphere, and once the rainfall, they will deposit with the rainwater, then it's also a main source from the nitrogen that we have. Based on this, we calculate the budget. We have the source from the atmosphere, from the population, from the land use. We also have the output from the stream water. We can measure the nitrogen concentration in the stream water, then we will understand the budget. One is from the input, the other is from the output. And here is the result. From the low disturbance, moderate disturbance, and the highly disturbed watershed. And here is the export of the nitrogen. So basically, so far, I think it is common if the water pollution is from the agriculture, then the nitrate will be the dominant species. If the nitrogen pollution is caused by the human activity, I mean the population, then it will be dominated by the ammonia. So it's quite different. In our case, you can find that for highly disturbed, the ammonia is the main species. For the moderate or low disturbed watersheds, the nitrate is the main species. But because nitrate is quite stable. So here is the concentration and here is the flux. Here is the flux. As our expected, we all know that with the people and the fertilizer use, then your water quality will be degraded and the concentration, the pollution concentration will getting higher and higher. It's very easy to expect. Therefore, we can find the retention ratio or the export ratio, which means that in lower disturbance watershed, only 18% will be export. Only 18% will be export. However, for the highly disturbed watershed, is around 42% of the nutrient will be export. So you will be getting increased. Getting increased, which means that the retention capacity is getting lost. It's getting lost. But that's still as expected. What we find in this study is that if we take the input as x-axis, and from the low disturbance, moderate disturbance, and highly disturbance, and the y-axis is the export, you will cut this curve. You will cut this curve, and which means that for the low disturbance, the slope is quite low, and getting higher and getting higher. So we are very happy to find this kind of the trend, because we find that it's around 6,000 to 8,000 kilograms per square kilometers. Below such kind of the input, our watershed will not respond with the input, with the increase of the input, which means that our ecosystem can sustain such kind of the input. After this point, after this tipping point, it will increase, the export will increase very significantly and very steep, with a very steep slope, which means that after that, your water quality will be degraded very rapidly. So I think in Taiwan watershed, maybe this is the threshold for our ecosystem to sustain the nitrogen pollution. But I have no idea for the other watershed. Maybe it is a good try to test such kind of the model or the thinking in Indonesia watershed, and we can find the difference threshold in tropical mountainous watershed and the subtropical mountainous watershed. So we also take the nitrogen models within our watershed, and we found that the nitrogen process within the soil is the main pathway to lead the nitrogen concentration in our spring water. So such kind of the soil ammonia storage and the nitrification and the plant uptake is the main loop. Is the main loop to generate the nitrogen to our streams. That's our another main findings in this study. So basically, I would say we still have so many problems, although we did some research talking about the erosion, landscape, chemical weathering, and the nutrient. But it still needs more. It still needs someone to, with patience and curiosities, to help, because there is too much, it's still unsolved. And I hope that will be the good, how to say that, is a good fundamental basis to help us together to collaborate with Taiwan and Indonesia. So that's the presentation all for today. Thanks very much.
Thank you very much, Professor Huang. I think we will do a parallel lectures, and the next lecture is Professor Yang Ji Chuan. Then the time is yours. Before Professor Yang started his presentations, maybe we can summarize the kind of outlook for future cooperations. What Professor Huang already did, I think, is enlightened us that erosions, nutrient transport, and also weathering is also a problem for us. Then the similar studies we have to do also in Indonesia to see the general pictures. Then the next time we can exchange apple to apple with the experience of Professor Huang. And I think now the time for Professor Ji Chuan Yang. Time is yours. Professor, excuse me, please use your microphone because we will record. Also.
Record.
Yeah.
Okay. I try. And it's called Ring of Fire. And in the beginning, they show the country had experienced a lot of volcano, and the people try to, I will not say survive, but try to deal with this, the volcano activity and create rich agriculture and different agriculture or different culture to live with this unique landscape in the world. And I realized the country is Indonesia. So at the moment, I don't realize why they pick up this country as a beginning. But after the field trip prepared from Professor Junior, now I realized. And it's such a beautiful island, have the volcano, but we cannot stop it, right? So the only thing we can do is deal with that and try to create our own survival lifestyle. Yeah. So another small story during the dinner with Professor Junun, he said the landscape process or geomorphological process is not only produced the natural desert, nature hazard, but also provide a natural resource. I fully agree this argument, and it's perfectly matching my talk today because it's also my concept or idea or feeling how to look at the landscape. Basically, it contains all of my research because my research interested focus on landscape system, mostly from the process-based perspective. But probably in the next few years, I will transfer to energy-based. But now I still focus on the process-based. As Professor Huang said, mostly our landscape system driven by two main drivers. One is climate, another tectonics. For example, the rainfall generates runoff and create erosion, and tectonic lift our rock and become the soil by weathering. And all of these drivers create our landscape, and we live in here. Not only human, but also the other life, like tree, like animal. However, for me, the system look like this approach. However, this natural driver sometimes too fast. So we create some natural disaster. For example, if there's too much water, it creates the flooding or debris flow. And as Professor Junun says, we are not only look at this process by the aspect or viewpoint of hazard, but also it's a resource. And vegetation, they use this source for the long time, long way from than human. For example, the vegetation will release some essence to enhance weathering to gather nutrient. So it's a common sense, right? But for the one of interesting of me and Professor Huang, we put the rock, the silica rock, spread into the farmer or forest, try to enhance this weathering and to capture the CO2 from air. And hopefully during this process we can somehow encounter the global warming. But I think it's still in a theory phase. So we need to do more research to constrain the efficiency or the rate of this process. Okay. So for me, these three approach can deliver into three like a scientific question. The first one, how can we observe this or predict this climate landscape change due to the environmental change, for example, like climate change. The second one, okay, if the process is too strong, too fast, how can we provide this strategy from the surface process? For example, how can we cannot stop debris flow, right? But how can we save our life from this process? And probably I don't have enough time to talk about the third topic, but we can discuss during the lunch, which is how to remove the CO2 from air, use the rock weathering. Okay, so just try to word in what I said just a few minutes ago. Okay, in the past few years, I focused on the unique landscape called Badland, and I try to use this example as a warming to describe my research interesting. So in Taiwan, the climate, of course, is the first driving force, especially in Badland. Badland, which means is a landscape unit without any vegetation. But in Taiwan, we have lots of vegetation, so it's very different phase compared with other Badland in the world. And the other point is our precipitation is very, very higher in Badland area. It's 2.1 meter. It's almost 3 times higher than other Badland area. And this 21 meter of rainfall concentrate during a few months, especially during the typhoon season. So 80% of them is concentrate on the rainy season. So this very high intensity driving force, of course, creates or generate many hill slope erosion. So the hill slope erosion is about 9 to 30 centimeters per year. It's quite that depth per year. So many soil lose from this area every year. But as if you met the Taiwanese, you can say, okay, how do you think about the Badland? They will say, okay, it's caused by the rainfall. But in this case, I will provide a new theory of this landscape. The Badland in Taiwan is not only driven by climate. Okay, you have a new idea, more idea than the normal regular Taiwanese now. The Badland in Taiwan is not driven by the climate only. In our study, we provide a new model, say, the Badland is controlled by tectonic. When we look at this figure, probably you can see the black area is Badland. And when we look at the panel D, there's a distribution of rainfall. There's no pattern between them, right? Which means the The rainfall creates lots of erosion, but it's not the main control factor for the distribution of badland. But who should take the responsibility? The uplift. So we use the DPS INSAR, the method of remote sensing, to constrain the uplift during this 10-year decade scale, and we find a pattern. The panel B show the distribution of uplift. The uplift in here can up to 40 millimeter per year, I mean that depth per year. So the ground uplift 4 centimeter per year is a huge. The average value in Taiwan is 5 to 8 millimeter per year. Here is 5 times higher, okay? We don't need to care about the mechanism now, but we see the pattern. And this pattern is matched to the distribution of to a badland. So that's our motivation. So I try to deliver the new idea to Taiwanese. The badland is not controlled by the calamine only, but the tectonic dust. Okay, there's a mechanism for this uplift. There's a 2 theory. One is anti-kite, and the other one is dipair. Probably you know the dipair, the moths, they gather the gas and push up to create a regional uplift. But there's still debate on this theory. Okay, and we find, so for now we find 2 things. The distribution of badland horizontally matching to the uplift, the distribution of uplift. That's the first thing. The second thing, the vertical distribution also matches some uplift history. For example, we can see the panel C. That's the distribution of vertical badland. He mentioned to 2 main terrace here. The river terrace, do you know river terrace? River terrace is mentioned to our uplift history. If you have a high uplift, the river will incision, so it form the terrace. So terrace means during that period they have the high uplift. So in this area, there's a 2 uplift history in this region, and vertically, the distribution of badland matching to those two time. So I have another idea, crazy idea. Can we use the vertical distribution of badland to rebuild the uplift history in here? So to fulfill this dream, I start from the digital elevation model. I don't know how to say. It's many words. Like anyway, the erosion model, because we cannot really understand the form in 2,000 years ago, right? It's too difficult for the human life. So we use this TEM to do some simulation. Can you pray it? Or I can pray. No, the previous one. Yes. Yes. Can you pray this one? Yes. So we start from the fret. You can say like a flooding fret, and we give some uplift. It start to erosion, disposition, and form the landscape. And we can measure some index from this landscape to create dimensionless of erosion and uplift. Next one, please. Next one. Yeah, for example, like this one. We use the S means slope, L is the river length, and the curvature on hilltop called CHT. We use these 3 parameters to create an index. Next, please. That's another example. In the panel, I don't know, the panel on the up and left part, you can see the illusion of one hill slope, and the bottom figure means the uplift history and erosion history. Can you pray? Yes. It should be more. Yes. Oh, now we create a mountain, and we decrease the uplift so it getting shorter. And we use this method to rebuild the entire uplift history in my area. So for the left panel, you can see many points. But the most important is the colorful point. We see from elevation of 20 meter to 100 meter. Let's see the curve. And the highest point is located on elevation of 40 meter. And this 40 meter can infer to 1.32 years ago, 1,000 years ago. So during that period, 2 to 1.3 thousand years ago, there's a very high uplift. And do you still remember the uplift pattern from P.S. Insar? He indicate the decade scale of uplift, right? And we know from this figure, there's all uplift in 1.3 thousand years ago. So it's every 1,000 years, it uplift and decreased. Probably this pattern can describe the mechanism of uplift. Yeah. Do I convince you? So from our method, we can do it, but there's no. I mean, there's interesting of geomorphologists. Okay, we are not like a GPS guy. They date the decade scale, but we look at more longer history from the landscape. Okay, next please. So we provide a conceptual model. In the beginning, it's all flat in my area, and there's a high uplift during the 1.32 thousand years. So the landscape of Belen form create a lot of barrel slope during that moment. And after that, they decreased until 20 years ago. So during this period, the Belen start to erosion and deposit to panel D. There's a sediment infill valley in here. And that's the reason why we still have a people living here, agriculture in here, because that special landscape unit. This valley is a plan for agriculture. So for my next study, I find this unit is the first time in Taiwan, and we try to find what's the role of this unit in this system. And luckily, I find a paper from Professor Junun, 2024. He provide here, the people will use this unit as the agricultural pump. They dig in it and put some water in it for agriculture. And we find a similar pattern or the practice in Taiwan. Okay, next one. So I switched the topic from the 1,000-year scale to a couple months. So my next topic is how to use this tool to monitor landscape dynamics, respond to individual event, especially typhoon and earthquake. As you can see from this figure, we have two kind of monitoring system. The geophone, the seismic station, colored by red. So he crossed from the mountain area to the river mouth, so almost entire catchment. The hydrological station colored by blue, you can see we have three. So we use this station to isolate the surface process. So it's not only the debris for rockfall, but also the flooding and the earthquake. that's my research site called Liu River. The erosion of this catchment is starting by typhoon again. So once you ask the Taiwanese what is the main drying force in Taiwan, you say typhoon is A+. So yeah, the entire, the annual rainfall is roughly 2 meters, and also concentrated in a specific month. So 70% of this rainfall concentrate on the river season. And the river's sediment flux, the fluvial sediment flux is about 100 million tons. It's not huge, but in terms of its catchment size, the ratio is pretty higher. And 2001, there's a paper in Science say in here, 90% of sediment flux caused by the event, typhoon event. So you can see this tiny catchment, they produce a lot of sediment during the very, very short time. That's my interest in. They push everything during a very short time. That's what we want to observe. Okay, luckily or unfortunately, we have a big earthquake last year, and there's the biggest earthquake since Chichi earthquake introduced by Professor Huang. So it's very serious, dangerous in Taiwan. And during this earthquake, co-seismic earthquake, there's many landslides occurred. And you can see during the few seconds, lots of landslide occurred and produced a lot of sediment into my channel. It's a good thing, bad thing. Okay. Based on the previous study, the table is quite busy, but I will try to deliver one information. They use different methods to measure the incision rate, erosion rate, but there's no single method or study say how about the co-seismic landslide and typhoon. So those two main driving forces in Taiwan combined together in 1 year. What happened? There's no study talk about this. And this is our opportunity to measure it. So after typhoon, just after 1 day, our people start to collect in the water and do the survey over there. So luckily we have a data image from 2018. So for us, it's like a best level. And we have a data from 2024, April, and go on. And during our observation, we have a 1 earthquake and 3 typhoon. So let's see what happened. There's some tool we use. We have as I say, I have 2 systems of station. Beside the station, we have a drone LiDAR, regular LiDAR, and people. People will collect the water and sediment on the river, on the outlet. Next one. Okay. I play some video from drone. So there's an image just after the co-seismic landslide. So it's another tributary. You can see the landslide dam. It's a new one. It's a fresh landslide dam. And still over there after a year. So there's 2 new landslide. So now we go up straight as O1. The spatial resolution is 12 centimeters, so it's quite okay. In terms of quantity, the volume. Okay, you can even see the border in the channel. Yeah. From this video, we can see many new form landslide occur in here during this probably 20 seconds. Okay. And we collect the data, sediment data. Okay. Let's see some result from drone. So that's the beginning to just after the earthquake. You can see the color means deposition or erosion. The red color means erosion. The blue color means deposition. Before the typhoon, I mean, just after the earthquake, the channel is dominated by erosion. It makes sense because the river just washed the sediment from the channel. And after one, we call Pum rain in Taiwan, but it's a summer monsoon. So after the first rainfall, you can see the erosion turned into deposition because a lot of sediment come from the upstream and landslide they deposit in the channel. So they turn erosion into deposition and increase almost 40 centimeter deposition in here. Just one, the monsoon event. And we see at least 3 landslide dam form during the event. So there's a 3 landslide dam. And one of them is, no. On the left side, you can see it's a very obvious one. The channel turned into red, right? So after the second typhoon, the deposition depth increased to 1.6 meter. It's very high. Especially here is in downstream area, not the upstream area. So you can imagine it's almost half full now. Then in the next one, it increased more, the half meter more in the next event. And next event, even more, 1.5 meter, which means even low, after a year, they still have many sediment come from the upstream, come from landslide. The catchment cannot digest this amount of sediment during the year. So how long should we take? From the experience of the Noto Peninsula in Japan, they say they need 20 years. So it's now our time to measure our area. Okay, beside the sediment transportation, I have another interesting is near surface groundwater dynamics. Because the typhoon not only trigger the sediment transportation, also the near surface water circle. So Sam, we have this system can do the same thing. Okay, let's skip this one. Okay, I talk to the result. We use the method called environmental seismology, and we use the ground shaking to rebuild the change in groundwater change. Does it make sense to you? Okay. Because you can imagine our soil, if it's dry, the velocity commit to each other is different. When it's saturated by water, by rainfall, the velocity decrease. So we detect this decrease as a process of the water level change. That's our basic concept. So on the very high mountain area, you cannot see the clear trend for this dynamics or change. My reason is because it's too high. It's about the 3,400 meter. The effect of typhoon cannot really reach that area. So it's our reference. In that height of station, the effect of typhoon is nothing. So when we go down, we see the pattern now. The red dots mean the change in groundwater level. You can see after the peak of discharge and rainfall, the DVOV increase and decrease. And it's very different from the previous monitoring because we have the gas station, the rainfall station, but we don't have a surface groundwater station. So for us, it's our new opportunity to use the method to quantify how they change during one typhoon event. And when does it recover? It need 41 days recovered back to the to the best level. When we go to the downstream, there's a station on the river terrace. You still can see the trend in it, and it saturates for a few days and decrease again. And it takes over 2 months to recover. So the recovery time increased. So when we go downstream, the recovery time increased. That makes sense to you, right? You can imagine you have a sponge that's full of water, and which part will be lose water firstly? The top, right? And the bottom, they will keep the water longer. Okay. The downstream area still need 2 months. Okay, this is like a summary. Our result is colored by green. Okay, so on the top of station, the recovery time is roughly 10 days, and the downstream area is more than 1 month. So for the groundwater, the up station need 10 days, similar, but the downstream area needed almost 2 months. So how can we use this information? 5 days of typhoon event trigger roughly 2 months of variation of near surface groundwater. Yeah, if you focus on the, like Professor Huang, focus on the chemical weathering or the water residence time, you should consider this. Yes. The second one, if you are interested in natural hazard, you will find some landslide occur during the sunny day without any rainfall. That's because the landscape still keep the water, even though after 2 months of event. Next one. So we start from the 1,000-year scale to months. Now I present you hourly time scale. So it's very, very short event. I mean, time in terms of timing. So how do you detect the sediment transportation? How do you do it? In the past, there's tons of research focused on how to detect the starting, or you could say onset, of the rock motion by the image or by the check dam. But the image, you cannot observe the bracket in the dark, right? It's a joke. Okay. You can see. And the second one, check dam is very expensive. You cannot build a check dam everywhere. So we provide a new method. It's very cheap and easy to operate. It's called environmental seismology. You can use acoustic data or seismic instrument like geophone or hydrophone to detect this movement. On the left panel, you can see the signal, the spectrogram from the normal period, which means no transportation. Once the rock start to move, you can see the intensity increase and some certain band, frequency band. And we use this frequency like a fingerprint to identify the different process. For example, I can give you an example. For example, you have a volcano, right? The volcano still have a ground shake. Do you know the frequency of volcano? How many? It's 110 to 100 hertz. Okay, it's very, very slow, very low frequency. So how about the wind of B? The B should be higher, right? How high? It's 800 hertz. How about the wind fall to the tree? This is 16 to 17. As hertz, we use this like a fingerprint to identify what kind of process. So for the turbulence, for the debris flow, they have prefer or like area, frequency zone. So we use to detect the onset or the starting point of the debris flow. But as I said yesterday, some of students joined the field trip with us. I mentioned one thing. We record this data every second. For example, the hydrophone, their sampling rate is 22K hertz, which means 32K hertz, which means you have a 32K data points per second. For geophone, it's 200 hertz, so you have a 200 data points per second, and you should measure the few years, right? That's a ton of data set you have. So the next question is, how do you deal with this mountains of data? You must use the machine learning method. Use the data science, right? It makes sense to you, right? Otherwise, your professor give you a 3-year video. Hey, watch. Point out the process. It doesn't make sense. So I provide you a method called Benford's law. Benford is a people, he discovered the pattern we call the distribution of the first digit. What is the first digit? For example, any member have the first digit. Every number has the first digit. For example, in this room, what's your height? 1 point something, right? Our first digit is 1. So the distribution of first digit of 1 is 100%. If I ask you, how about your weight? It's a very rule, but how about your weight? Oh, someone start from 5 to something. So it still have a distribution, right? Once your data set is bigger than 12,000 and the range cross one order, there's possibly to form the first digit distribution, which means look like this curve. The first digit of 1 occupy like 30% of data set and decrease to roughly 4-5% for the first digit of 9. So if you once got this distribution, which means you have a high energy event occur. High energy event, probably typhoon, probably earthquake, probably the debris flow. Okay? Okay, let me show you some example. Okay, this is some application of this distribution. The population of a major city in Spain also follow this distribution, and people use this distribution to dictate the starting point of earthquake. For me, I combine 3 sessions of sound, the video, and can I play the first one? So let's hear some. The first one. Some recording from my river. Not this river, but Liu River. Can you hear something? Yeah, a little bit. Very gentle, chill. Yeah, do you hear it? No? Again, please. Some river? Yes. So let's hear some debris flow, the second one. So you can hear the rock compared to each other. Okay, thank you. Now we play the video, the whole video. take this like a background. Okay, here we have a 3 session of video. The first like 5 minutes is mean nothing. And after 5 minutes, you can see the amplitude start to vibrate, right? And it back to normal. And in the panel on the bottom, you can see the amplitude distribution and first digit and normalized first digit. But I want you to focus on the central one, the distribution of first digit, to see what happened before the event and during the event. Can you pray? Yes, thank you. Okay, so we start from nothing. So the first digit of 3 is occupied. And the distribution of the amplitude is focused, is concentrated on the certain band. And yeah, you can see the distribution change, turning into first digit distribution, which means the first digit of 1 occupy the entire distribution, and the amplitude start to jump in. And back to normal. So we create a new index. Once we got this distribution, this is event. Okay, so let's see our result. There's a research site. Next one. Thank you. So our research site is still in Liu River, but we pick up the upstream area. Okay, that's our station. So we have a hydrophone, which means the microphone like this one, but we put into the water that can record the sound. And the sampling rate 32K. Every second you have 32K data. And we have other independent data called water stage, water level, and the image, the camera. Okay. So you can see the blue line means the water level. So there's a 2 event, we know that, in 2019 and 21. And based on our result, we find the band follow distribution as called first digit distribution. If we obey to this distribution, is colored by green, otherwise red. So we observe many signals, but they all concentrate on that period, certain period, just few hours. So probably our index is okay. So now we need to confirm this thing. So next. So we focus on those 2 periods and check their spectrogram, like a normal traditional way. And we find, okay, they do have an event from the panel E and F. That's an event. You can see the clear pattern. And from our method, we find the panel C and D. In our method, we find a similar pattern with a traditional way. So we'll somehow confirm our method, okay. And we are not only provide a starting point and ending point of event, we can further separate the type of sound. Because during the deep-freeze flow, there's many different sounds, like a rock, like a turbulence. For our method, we can separate. So we can make a proportion for this sound type. And from this study, it also created a new direction from the old study. During our observation, we find it's not only water, it's not only sediment will transport during the event. The wood will transport during the event. So my next topic is how can we detect the wood during the event? Do you have any idea? Wood. We can find the people collect the wood, but it's too dangerous, right? Remote sensing is a good idea. Yeah. So there's another method called deep learning. We can detect video, image, and we're training the data set. For example, for this one is cat. Okay, so we give him a. So we already have a Chinese. Sorry, we don't have. The people already have a Chinese set for cat. So we upload our video to the data set, and he can identify. Okay, this cat. How many percent of probability is cat or not? So from this data set, they can say, in computer, they say, okay, how many percentage is cat? Of course, for human, we can say it's 100% for cat, but computer cannot say that. So we should set a threshold, say, okay, over 30%, over 40%, is a like threshold can accept the result. So for computer, let's say 44% of probability is a cat. Okay, it's okay for us. So now we try to use this method to our data set. But firstly, we should build our training set, right? Unfortunately, in Taiwan, we don't have a wood training data set. In the beginning, I said, okay, just use it and upload our data. But no, we need to build out the training set for ourselves. So, next, very short talk. We firstly to identify where has the wood. During a typhoon event or during a flood, there's a 5 kind of wood. On the slope, beside the riverside, in the stream, on the coast, or on the bottom of water, like a lake or ocean. For us, we only have an opportunity to observe the wood deposit on the land. So on the hill slope or on the riverside, we can detect it, or in the stream. Otherwise, we cannot really take image from them. So we use those 3 kind of wood as our target. So we collect the data from the target. So firstly, we build out our training data set by EuroVBA. Probably you already heard it. So the method is called object detection and the segmentation. So you can identify the location or the area of the wood. So we already trained 2 kind of detection model. And here's the result. For the object detection, we can detect over 90% of wood in the stream, on the riverside. So for the location, it's very easy to identify. But for the area, how many wood, how many volume we have is very difficult. For our training data, we only say 70% of the wood we can detect precisely in terms of the area. But for our dream, area or volume is much important than location in terms of science, because we want to constrain or calculate the carbon storage volume, right? The wood contain the carbon inside. So once we got the volume, we can calculate the storage of carbon from that result. So we are still trying. Okay, summary from the previous one. Question. Do you have any short question? Okay. Do I have the next one? Oh, thank you so much. That's my talk today.
So, thank you very much. It is very interesting, he make a very detailed study on soil erosion, and he actualized the general geomorphological concept of aggregation and degradation with the actual direct measurement in the field and then back to the big concept of watershed management and so on, which is really interesting for us. Yeah. Then now it's time for question and answer for all of you who are having question. Please raise your hand. Nobody asking? Okay. How many? Mbak dibantu Mbak Sopo. Okay. Start from the front. Yes. Maybe I limit with three. Depan ini Mas. Mbak. I limit 3 first, then the next 3. Otherwise, the lecturer will forget your question. Because if it is too much. Yeah. Please.
Good morning,
Introduce
Professor
yourself,
Junun,
please.
Prof. Huang, and also Dr. Yang. Thank you for the opportunity. Let me introduce myself first. My name is Nadia. I'm a postdoctoral, I'm a doctoral student at Faculty of Geography UGM, and my research is about tsunami modeling in Sumatra Island. Maybe we can share some related topics with your presentation. Yes, from your presentation, maybe you can share from your perspective what would be the most effective way to bridge and communicate disaster-related research findings to policymakers, particularly the government, so that they can clearly understand our research findings and effectively apply it. And I would also greatly appreciate if you could share insights from the experience of scientists and the government in Taiwan regarding this matter. In addition, could you also elaborate on how and what you consider to be the greatest challenge faced by scientists in developing solutions to address the massive erosion problems and also rapid uplift occurring in Taiwan? And the last one is how do extreme events such as flash floods or post-seismic flows affect the threshold of bed load initiation, and how can we detect it under such conditions? Thank you.
There's no question. Do you have a comment? Yeah. Yes, this.
Your background is tsunami detection, right? So I have some experience about the tsunami warning system when I was studying in the previous institute. They installed the fiber offshore on the offshore to detect the variation from the earthquake on the sea. So once they got the variation, they can detect when. But it's installed in the subduction zone, so it's very deep. So they can see the change in the very beginning, and they send the signal to the land to warning to initiate the system. And the other aspects, how can we do from for the public, right? And I also see another aspect for this warning system, early warning system. The people can use their, I think everyone has a phone. They use the phone to take an image and transfer to the text, upload to, there's a central system that can deliver the message like a file to the local people. I think that's one of what I know about the early warning system. But it's not only for the tsunami, for the flooding, for the landslide, earthquake also. For the policy, probably. I don't know about the policy.
Well, it is difficult to to answer your question about the policy, not all the experts who really doing very deep on a certain measurement, observation, and so on, and transfer into policy. It is another sciences. I think I couldn't answer. Yeah, sorry for it. But your concern will be also our concern also.
It's okay, Prof. Thank you.
You're welcome. And the next one, Mas yang belakang.
Check. Good morning. My question is for Professor Huang regarding eutrophication. Before that, maybe I would like to introduce myself. My name is Muhammad Aki. I'm currently studying disaster management. And regarding eutrophication, as Professor Huang said, it's a growing phenomenon globally. So maybe I would like to understand how the first thing is how the early warning system that could be cost effective in Taiwan, and also how Taiwan has addressed this situation, especially in eutrophication regarding watershed management. Thank you.
Komataki? I mean your name?
Taki.
Aki, okay. Thanks for your question. Yeah, it's a long story. 20 years ago, in fact, all the Taiwan rivers are highly polluted, because in mountains, we have village, we have agriculture. And in the middles, we have the livelihood. In the downstream, we have the industry. So 20 years ago, most of the Taiwan rivers are highly polluted. And then our government tried to improve the water quality. The first thing is that we limited the chemical fertilizer. This is the first thing, because we found that the crop, in fact, do not need so much chemical fertilizer. So we have a strong regulation. According to your land area and according to your crops, we limited the fertilizer. This is the first thing. I mean in mountain area, okay? And the second thing is that we limited the area for agriculture. We limited the area. If it's not illegal, then the government will fine it. And the third one, we try to do some flow trip, the buffer zone. Buffer zone probably is the most cost-effective way to prevent the pollution. That flow trip in Taiwan basically is around 50 meters, is effective distance. It means that the river, we set the buffer zone around 50 meters. During this riparian zone, there is not allowed for agriculture for anything. Then the water quality will be improved. For the downstream, the urban area, I think the sewage system, the wastewater treatment is the most effective. And of course, the point source pollution, like the industrial, you need to find it out firstly, and then you have the wastewater treatment. Then you will get the very significant water improvement in urban area. So after the 20 years ago, our water quality, the water quality in our streams improved very significantly. Yeah.
Okay.
Thank you very much, Professor Huang.
You're welcome. The next, the lady in the.
Okay, good morning. My name is Adintan Pitaloka from Environmental Science Master student, especially from Geoinformatics and Disaster Risk Management and Spatial Planning. I have a question for Mr. Huang or maybe Mr. Yang. And the question is, the rainfall is not the main factor cause the erosion, but Mr. Yang said that the uplift is the main cause. But how can we predict the uplift movement? And then if we use the remote sensing, what kind of image that we can use? And then is it enough if we just using digital elevation model to analyze? That's from me. Thank you.
Okay, I think I can try to recap your question. Is how can we use remote sensing is enough to detect the deformation of this crust, and probably this deformation will cause some damage. So let's separate this question into two parts. What kind of deformation you mentioned? The first one could be the very short event like earthquake. So the people use different methods to detect earthquake. We can detect, but we not can predict the earthquake. So they use GPS, they use geophone. Big one, probably you know the mechanism of earthquake. The fall will accumulate the stress and reach some point and will respond to create the shaking. And before they reaching the point, the GPS velocity will increase. The shaking from geophone will increase. So it's like a signal. We can really warning about the earthquake. But as I say, we cannot really predict it. We cannot try to find some signal. And the second one is deformation, which belong to the very long term of movement. Like I say, the movement is every 1,000 years. There has one pulse, and the pulse can occupy few hundred years, right? So you cannot really detect this movement, but he create our landscape. So I will say, for the erosion, yes, in terms of geomorphology, we say the uplift is the fundamental for erosion, because erosion try to catch up the speed of the rate of uplift. So in a long-term equilibrium system, the erosion is trying to catch up the uplift rate. So there's a reason why I say the uplift rate is driving force in my area. But it also depends on the time scale. Of course, I will give you an example. During the 3 days of typhoon, uplift is nothing, right? The rainfall dominates everything. So I will try to say the scale is matter. So there's a reason why I try to recap the question into different parts. I hope I answer your question.
Yeah, the scale and also the time period. Yeah, keyword.
I think I can add some sentence. Basically, I would say remote sensing is very, very powerful because it can collect the signals and within a large extent. So it could be everything. If you can have some algorithm and if you can select the right spectrum and you can form the index, you can capture the signal. That would be very powerful. So I think that would be the highly potential technique if you can combine the AI and the remote sensing. This is the one hand. Personally, I encourage this field. On the other hand, as Dr. Yang said, even the signal, even we can detect some signals, please be careful. Sometimes the signal are a mixture from the different processes. Then you still need to know the domain knowledge, what's the signal really reflect the process. So if you can combine the two perspectives, I think that would be very strong and can solve a lot of scientific questions. So that's my personal comments.
Okay, another question? Please.
Okay, good morning. As Mr. Huang and Mr. Yang said before, there are a lot of similarities between Indonesia and Taiwan, and we are located at the Ring of Fire, high rainfall, tropical climate, etc., etc. But of course, there are also a lot of difference. We don't have typhoons, and Taiwan have. We have very active volcanoes compared to Taiwan. So the question is, do you think we can replicate your methods in Indonesia? And if so, what are the things to consider or to modify if we want to replicate your methods in Indonesia? Thank you.
It's a very good question because, as I said, we have many similar environmental settings. And as you questioned, in fact, we also have many different in many aspects. So just because the reason, that's why it's worth to try, you know. If you do not try, you don't understand the difference will cause that the method is capable or not, you know. So one thing we all agree that we have the similarity in environmental settings. On the other hand, we all know that in fact we still exist some difference, as you said, the rainfall, you do not have the typhoon, so the rainfall intensity are not similar. So there are two worthwhile points that we can highlight. The first one, as you said, the method is capable or not. The method can use for different environment is very worthwhile to try. On the other hand, if the method is not workable either in Taiwan or either in Indonesia, which means that it can set up a new hypothesis to set up a new theory and the new methods. So either from the straightforward or retrospective, this is very worthwhile to try, even we have the difference.
In my opinion, because my methods, I think they are all capable to other catchment, because it's why I try to build up my career. I want to introduce my method or approach to other catchment, other country. That's what my goal. So the presentation from today, like you said, the hydrophone, geophone, the LiDAR, they can apply to everywhere. Yeah. So for the tool phase, I think it's okay. And for the topic, I think we still have a lot of similarity. For example, yesterday we've been to some location. Sorry, I don't really got the name, but the river along the volcano, and I see lots of opportunity from that side, because the eruption from volcano, they create a lot of deposition along the river side, and river incision bring lots of materials. It's like the same the case from Liu. Lots of sediment enter the channel, and after the big event, like a rainfall event, you still have a 3 meter of rainfall per year, right? There's rainfall, high speed or high intensity flood, wash the sediment to the downstream. And you have industry in the downstream, the miner economy in the downstream. I saw them yesterday. So for first step, build up the warning system for them is very important, and we can fully apply the system to that. This is just one of topic. And I also want to add one point, because it is our first time to this country, so we still have many things need to learn. So because we are lucky, we have Professor Junun and Dr. Alok, they bridge us, and because they know here, and then they know both sides, Taiwan and Indonesia, very well. So there's a reason we can catch up the specific topic with the 2 days. But I think you guys come from different backgrounds, so you have a different interesting. But for now, I can just say that, yeah, we already have a common interesting, just 2 days. Yeah, so we still have a long way need to go. Yeah. Thank you.
Another question? Man, in front of you. Okay.
Good morning. My name is Dini, and I want to ask something to Professor Huang. Based what you explained, there are three parameters about erosion, which are population, rainfall, and land use. My question is, between those three parameters, which one the most dominant based on your experience? Thank you.
Sorry, pardon. Which one is what?
Dominate.
Which one is dominant? Okay. Thanks for the question, Vinny. It depends. It depends. In Taiwan, in mountainous regions, the land use, the agriculture is dominant. In urban, the population must be dominant. So it depends. So far around the world, in Japan and in China and in Taiwan, they also follow such kind of the pattern. Even in US. So I'm not sure in Indonesia, but we can try it. Basically, in mountainous area, agriculture is dominant and then nitrate is dominant, is the main species. In downstream area, population dominant, then ammonia will be dominant. So even they are all nitrogen pollutions, but you need to have the different treatment to improve the water quality. So I think this is quite important. For Europe, I know there are many living wood, like the cattle, like the sheep, maybe another stories, but yeah.
Okay. Still have some question to discuss?
Thank you for the time. I'm Akbar. I'm from Master Study in Geoinformation for Disaster Management and Spatial Plane. I have simple question about cold deformation affected landslide. Because I'm research in co-seismic landslide. Thank you.
So what's your question?
Cold deformation affected co-seismic landslide.
Co-effect.
Yeah, effect.
Co-effect by the co-seismic landslide.
Yes.
But in terms of who? What's your target?
That's because I want a deformation. I have a plan. Deformation has a control factor for co-seismic landslide.
Control factor.
Yes, because my research in susceptibility landslide.
Susceptibility. That's an interesting topic because I also want to do the same research in the next presentation. Thank you. I'm very physical geographer, so I'm not really understand the social system. Probably Professor Huang has a more experience, but I can share some my opinion because I want to build out the system. It's a network. Probably we can share to each other our experience. How to deliver the physical impact, for example, like a co-seismic, lot of volume enter the river. They change the transportation rate, the sediment concentration, and also nutrient concentration. And this impact, how to deliver this impact into a society system. This I try to do in the future. So I'm still thinking because from this side to this phase, there's no approach. We just talk about, we use the quantitative way. I try to use quantitative way to do this one. But firstly, we need to identify the target for the social system. what will be effect by physical forcing in the social system? Population, the agriculture, production, I don't know what else. But probably I will choose some of them and as our target to link the physical process, but still very physical thinking. Probably you ask some people working on the cultural geography or economy ecology geographer, he will give you a totally different idea. Yeah, that's what I know.
Okay. Yeah.
Maybe just one comment. Since you are talking about the landslides, in my personal perspectives, there are two strategies you need to go, you know. The first one is from the hazard perspective. From the hazard perspective, then you need to prevent it, you need to mitigate it, and you need to, when the landslide coming, you need to have some actions, you know, and then recovery. That's for the perspective of the hazard. However, if you put it into a large framework, for example, the socio-ecological system, you just, the so-called socio-ecological system, which means that the society always take the ecosystem service from the nature system, even the hazards. We always take the ecosystem service from the nature system. So the landslide dominated area, in fact, the landslide will always occur and occur and occur. Just several years, it will come again and again and again. Therefore, in such kind of the socio-ecological system, then you still can gain something from it, like the June said, the hazard is the resource. Just the Dr. Yang said, the landslide maybe put something into the stream and re-regulate the ecosystem service in aggregate the ecosystem, and then the downstream. So, from your questions, I would say there are two perspectives. One is from the hazard perspective, you need to protect, you need to mitigate. But from the large social ecological perspective, you need to know what kind of the ecosystem you can earn from the landslide, such kind of the process. So you may get the different results.
Okay. There's others from all the person who give a question in the center. Who is the side wing, left and right? No? I think there's enough for the presentation. So thank you very much for your presentations. And maybe both of you can introduce your institutions. Some of them maybe would like to collaborate their research with you and with your institutions. Of course, under the umbrella of Gajah Mada and NTU cooperations. Can you explain, or you have? Huh? Oh, yeah, you can. You can, yeah. So it is just only 10 minutes, 15 minutes additional information because maybe not only me who like to continue our cooperations, maybe some of you want to make a collaboration with them, then it will be good information for you all.
Sorry to disturb you. 5 minutes, okay?
interested to work to continue this meeting, maybe I will invite you in the research center tomorrow afternoon. Tomorrow afternoon. So please be free to contact the contact persons in the flyer. Thank you very much. So I think this all the presentations, and again I would like to express my thank you to you, Professor Huang and Professor Yang, and thank you for your all the audience who already follow this general lecture. Thank you very much. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh.
Thank you everyone for exchanging the question and insightful discussion. Before we officially close this event, I would like to invite Prof. Junun once again to give the appreciation for the speakers. Please coming Prof. Junun and Professor Huang and Dr. Yang. Thank you, Prof. Junun. Thank you, Prof. Huang and Dr. Yang. And thank you for all the participants. We hope you found today's guest lecture inspiring and open many research opportunities. And we look forward to seeing you at the future event. Have a wonderful ahead. Wassalamualaikum warahmatullahi wabarakatuh.